us start this lecture with a thought process from Albert Einstein. Everything has changed except our way of thinking. It is very important to ponder about this statement because it is having pregnant meaning. And before starting discussion on the today's lecture, let us recapitulate what we learned in the last lecture. I had initiated discussion on the phase change processes, and of course, before that we defined a pure substance, and we have considered the water as a pure substance, one of the pure substance, and looked at the processes of vaporization, sublimations and other things using the experimental setup, what it can be used, and also we depicted the processes in PV diagram and TV diagrams. We have also seen the limitation of this diagram for describing the processes, right. Then we also looked at another interesting diagram, what we call it as basically phase diagram, where all three phases can be described, that is basically P and T, and when we combine all those diagrams, we got a three-dimensional view of the phase change processes, which depicts all the aspects like liquid, liquid vapor, solid and liquid solid, and superheated vapors and other thing. And we have also distinguished how this water phase diagram or water is different than that of the other substances, particularly the water, which is having peculiar features is that when it condenses into ice, its density decreases, unlike other materials, other pure substances, where the density of the solid is higher than the liquid. In case of water, the density of ice is less than the water, that is why it floats. And that is the reason why we have evolved, or the nature has evolved into so many species. Otherwise, ice could have submerged on the bottom of the sea or the river, and which could have not melted out to form the ice, so that ice age could have not overcome, even though the solar energy and sun was giving enough heat to the earth. So, beside this, we have also looked up about the limitation of the what you call data being represented on a diagram, and then we looked at the table, steam table particularly. We have not looked at refrigeration table, but you can use the refrigeration table for solving problems. And we have taken some examples also to how to solve these problems, and I had also discussed the Moeller diagram, which was a very compact diagram for the steam, which were using earlier days on the subfloor itself. I mean, subfloor means basically in the industries. For example, you are running a power plant, steam power plant. So, you can use that, and there the processes can be, and we will spend little time again on this diagram and what is the importance of it, that is the Moeller diagram. In this case, if you look at the diagram is shown here, and on this side, if you look at enthalpy being plotted, like on this. So, if you look at this line, the is basically saturated line, right, where saturated vapor line basically, where x is equal to 1. If you look at this is x is equal to 1 this point, and the x is the quality of the steam, and it goes on changing, like decreases, and all this line is constant quality line. For example, this is 0.95, this is 0.9 and then 0.8, all those things. And these lines, these blue lines, if you look at, for example, this correspond to 500 bar and this is corresponding to 200 bar. This is the isobaric, line, you can say, or the process will be isobaric, 100 and 50, 200 bar and 10, 4, 2, 1, all those things, it goes on to the 0.01 bar kind of things. Beside this, you please observe this diagram, which is little complex in nature as compared to other diagrams. And these lines, which are green lines, if you look at, this is your 50 degrees Celsius and this is 100 degrees Celsius, 150, 200, this line, I mean, these green lines, it goes on temperature till 800 degrees Celsius. So, if you look at this is a very compact process. For example, like you can use this quickly, calculate what would be change. For example, if I take a plot over here 100, let us say bar, and I will say that my given point, I am just taking for the simplicity, like let us say this is the point which is given to me, like that means this correspond to, this will be what, like this is my 100, right, and this will be maybe 120, 40, 60, 80 and 100. This will be, what will be pressure here at this point? Pressure will be 120 bar, right. Okay. And what will be temperature for this point? That will be your 650 degrees Celsius, right. And there is another point I am getting, like let us say arbitrarily I will take corresponding to, let us say, something 300 degrees Celsius, right. This is another point, this is 300 degrees Celsius, and pressure, if you look at this line is corresponding to 100 bar, right. Now, what are the process? Process could have been taken place like this, this is my process, let us say. I want to evaluate, I can directly evaluate what will be my enthalpy. I will do this line, find it out what will be change in enthalpy. Similarly, I will find out what will be my enthalpy. I will draw a parallel line to this, parallel to the entropy, like this thing, that will give me directly enthalpy. Here it will give me enthalpy. So, I know the change in enthalpy process. But however, is this process is reversible or not? Suppose you say that this process which is not really reversible, and if it is reversible, right, then the entropy could have been constant. So, if I draw a vertical line here, I can draw a vertical line here, right, and then I can say this is the pressure line, okay, the same pressure. So, this is your basically the what you call, of course, I could have drawn that solid line, this one, and this could have been a dashed line, right. Then this is basically the isentropic process, and this is the ideal process, okay, and this is actual process. So, I can know that how it is happening, because the entropy here remaining constant, right, and it should be vertical, and then I know how it is. From this I can evaluate what it would be, efficiency if I want to find out. That is one way. But another way, suppose I do not know this process in between these two states, I can say, look, it is being what you call expanded here, because from high pressure to low pressure, and then again I can go by the constant pressure process, right, as a constant pressure line, and I can reach there. So, it will not only give you the data, because it will not only give you the data, but also it will tell you how the process can be, just knowing the process, this thing. So, therefore, it will give a visual understanding of what is happening, and also it will give you data, but problem is that how you will get a data here, which is, because if it could have been here, it could have been easier for you to get the data, but in between you will have to approximate it. So, therefore, there will be an error which can be incurred, because of, and as a result there will be an inaccuracy in data. And of course, one can use these things, and this is quite interesting and can be utilized for what you call quickly getting the data. It may be inaccurate, but however, in the plant, like you want to take a decision what is to be done, like then naturally you will quickly get into this, and you can visualize the things very easily. Even till today also it can be used, but however, people have now computerized, instead of this thing they can go and put the data and quickly get. So, that is happening. So, this can be computerized and can be used. So, now what we will do, we will take another example just to find out how we can use a table to get the thermodynamic properties data. For example, like we need to calculate V, that is the specific volume, internal energy and enthalpy H of a steam at 200 degrees Celsius with a quality of 0.8, right. Okay. So, and determine the pressure of the steam. Now, in this case, like the temperature is given at 200 degrees Celsius. Of course, the quality is given 0.8. So, what table you will have to use? If you look at, you are now exposed to three kind of data tables, steam tables, right. One is the saturated temperature, steam table, saturated pressure steam table, and superheated steam table. Am I right or wrong? Is it I discussed in the last lecture? Saturated steam table and saturated pressure table, steam table, right. And one can also, we are having superheated steam table, where you will be getting that this what you call two variables had to be given, pressure and temperature, right. And so, how we will determine this, right. So, what will they? This you will have to use basically a saturated steam table, steam temperature table, and from that we can have the data what you call pressure, because this pressure is basically, what is this pressure? This pressure is nothing but your saturated pressure at saturated temperature of 200 degrees Celsius, right. And correspondingly you will get Vf, which is the liquid specific volume, which is very very small as compared to the vapor specific volume, and you will get Hf, that is what you call liquid enthalpy or saturated liquid enthalpy, and the saturated vapor enthalpy is 2790.9 kilojoule per kg, which is much higher as compared to the liquid. And of course, Hg minus Hf will give me Hfg, that is the latent heat of vaporization, right. And as X is given to you, so you can very easily find out what will be the specific volume by with the quality 0.8 from this data Vf and Vg. So, we know that the formula is V is equal to X Vg plus 1 minus X Vf. You just put these values here, right. that means, if you look at these values, you can use from here, you substitute in this place, and V z you can substitute in this place, and you will get these values very easily, right. And enthalpy also you can evaluate similar manner, right. I know the quality. If you look at this, quality is given and this is given and H f is given, you just substitute and get. But now question arises, how will get internal energy? Of course, there might be some steam tables which might have given the internal energy, but however, in your exam and in the textbook what we are following, the what you call internal energy U is not given in the table. So, how you will have to evaluate? You will have to basically evaluate using from this data, that is enthalpy I know, and from that I can get the internal energy is equal to H minus P V, and P corresponding to the saturated pressure whatever is there, and you multiply it by the V and you will get that, right. So, by this we can use the what you call the steam table to evaluate properties, and in the steam table you can use the saturated steam temperature table or saturated steam pressure table, or you can use the superheated steam tables, right. So, what we will do now, we will have to look at the superheated vapor, and superheated vapor basically will be in the vapor region. In this case, temperature and pressure are independent properties, unlike the saturated vapor or the saturated liquid. In the, if it is a wet mixture, if you will be given one what you call either the temperature or the pressure, then you will be good enough, or you are in a position to find out the properties. For example, if it is temperature is given here, so this properties what it would be, and if it is other temperature is given, so you can find out, and if you are given the pressure, saturated pressure you can. But in this case vapor region, what you will have to? We will have to basically know the two properties, both the temperature and pressure has to be given, right. Then only you can evaluate the properties. For example, this is the superheated vapor table where the pressure is given, right, and that is the 300 kPa. Of course, corresponding to this pressure, the saturated temperature will be 133.55 degrees Celsius. And then you are given the data at different temperature for a particular 300 kPa kilopascal, that 150 degrees Celsius, 200, 250 go on. I mean this is the short table what I have shown, and here what you will see? You will see that V, that is the specific volume, is given in this way. What you can observe from this data? What you can observe from this specific volume data? That means it is increasing with the temperature for a particular pressure, right. And similarly, the enthalpy, it is also increasing, and entropy, it is also increasing with the increase in temperature. And you can get various table on that, like at different pressure, and so that from this you can find out. But if you compare this superheated vapor table with the saturated vapor table, you can observe this one, that always at a given temperature, right, the pressure will be less than the saturated pressure, right. For example, like if you look at this diagram, right, if it is let us say I am operating at this what you call some pressure here, right. Let us say this is the pressure, I am looking at temperature. So, vapor means always it will be here, which will be what you call the lower than that this temperature if you look at this temperature. Similarly, if you look at higher temperature, that means the T always will be for a given pressure, the T always will be at a more than the C saturated, and the specific volume we have already seen, that means the at a given pressure it will be more than than the saturated value, because this is the saturated values and this will be higher than that the specific. So, also the enthalpy, so also the internal energy will be higher than the saturated vapor values. So, we will take an example like how we can use that. So, for example, like determine the temperature of water at state of pressure equal to 0.5 megapascals and enthalpy was 2929 kilojoule per kg. How I will know whether it is corresponding, whether I will have to use the superheated pressure table or I will have to use whether I will have to use the saturated pressure table or superheated table corresponding to this pressure. How I will know? Because the pressure is given. If pressure is given, of course, the enthalpy is given here. I have taken a very simple example to illustrate how to go about, because that confusion may arise in your mind, which one I will have to choose, because there are various tables, what we have looked at till now, 3 tables. One is superheated steam table, other is saturated temperature table, steam table, and saturated pressure steam table. Of course, in this case the pressure is given. So, therefore, and temperature is not given. So, you need not to use the saturated saturated temperature steam table, right. So, you will have to use saturated pressure steam table. Am I right or wrong? So, now whether you will be using the superheated or not, how you will arrive at? What for that, what we will have to do? You will have to first take the saturated steam table corresponding to the pressure of the what you call 0.5 megapascal. We get these values. HF is 640.12 kilojoule per kg and Hg is 2747.5 kilojoule per kg, right. Now, from these, can you guess whether this data, whatever is given this example, is in the saturated regime or it is in the superheated? Definitely it is superheated, because the H is given here and which is 2929 kilojoule per kg, which is greater than the Hg, right. So, therefore, it will be superheated steam table, or the steam or this condition is occurring at the superheated regime. So, therefore, you will have to use the superheated steam table. Just to illustrate this point, I will just say that you are at here, right, at this point, and because H, this H is greater than the Hg. So, hence the steam is in the superheated region, and from superheated steam table corresponding to 0.5 megapascal, we will get these values. Like that means, at 200 degrees Celsius 2860.4 kilojoule per kg, and 300 degrees Celsius the values of Hg is 3067.2. That means, my condition, that is H 2929 kilojoule per kg will be in between these two regime. That means, if I say this is my temperature, this I need to find out Hg here, right. At this point I need to find out. and this is given to me, right. What is that? That is 2929, right. So, from this what I will have to do? This is basically not known. So, you will have to find it out. How I will do that? We will have to use what? Linear interpolation, right. And if I do a linear interpolation, I will get T is equal to 200 plus 68.6 into 100 divided by 3067.2 minus 2860.4. If you look at what we will do, we have earlier seen that how to get that. If you look at the slope here, the T minus 200 is divided by the 2929 minus 2860.4 is equal to 300 minus 200 divided by 3067.2, which is corresponding to 300 Kelvin, and 2860.4 kilojoule per kg, which is corresponding to the 200. So, from this I can get this relationship, I can evaluate, that happens to be 233.17 Kelvin. Keep in mind that here we are doing an approximation, there will be some error, because you cannot really relate this thing linearly, right. However, if the data points is not interval is not much, then that error which will be incurred by this simplification or approximation will not really matter much. So, therefore, one can use it. So, what we will be looking at, we have looked at till now saturated saturated condition, saturated steam table, and we have looked at superheated steam table, and also there is some table for the compressed liquid, right, and compressed liquid table will be available, but in some places it will not be. So, now if it will not be available, how to use compressed liquid? Do you know what do you mean by compressed liquid? Is basically subcooled liquid where the pressure will be higher than the saturated pressure corresponding. Now, compressed liquid depend on the temperature much more strongly than they do on the pressure, right. What people have found, if the pressure will increase 100 times, the change in properties will be something around 1% kind of thing. So, then people say that you are not bothered about it, right. But however, it is more dependent on the temperature. So, a compressed liquid may be approximated as a saturated liquid at a given temperature, right. Because if I know the temperature, I can go directly to the saturated steam table, and corresponding to that temperature what is given, I can use the properties for my calculation. For example, like if you look at this at a given pressure and temperature, what you will have to do? You will have to go to the temperature and go to the saturated temperature steam table. For example, if we are considering water, or if we are considering other things like carbon dioxide or some other gases or some other pure material, then you can go for that. So, what you can use, that V specific volume has to be evaluated at what? At saturated temperature condition, right. Similarly, for the internal energy and enthalpy, but if you look at and entropy you can evaluate, but among all these properties you will find that enthalpy variation due to this you are neglecting the pressure, then will be little bit higher. So, therefore, one can think of how to do that. So, at a given pressure and temperature, your pure substance will exist as a compressed liquid if T is less than the saturated what we call temperature per a particular pressure. And if you you can generalize it, this property is y, and y can be specific volume, or it can be internal energy, specific internal energy, or specific enthalpy, and it has to be evaluated at saturated temperature from the saturated temperature table. And if you want to improve this what you call you want to improve the value of the enthalpy, which might have been this thing, then you can use the enthalpy kind of things. So, just to illustrate this point, what you call like that how you can evaluate. For example, if it is 500 kilopascals and you look at saturated temperature will be what you call 151.83 degrees Celsius. But however, if the temperature is given 75, 500 kPa and 7, this will be definitely compressed liquid, and you will have to evaluate properties not corresponding to 500 kPa, rather corresponding to the 75 degrees Celsius, and then you can get these values, enthalpy, entropy and other properties corresponding to 75 degrees Celsius. And if you want to what you call accurate data for the enthalpy, one can evaluate, one can improve this evaluation by considering that what you call enthalpy at the saturated temperature conditions plus V f at the saturated temperature into P minus P saturated pressure at the saturated temperature, what is given. So, that these are the what you call, this portion is additional things you can help in improving the quality. If you look at you can evaluate these properties, you will find this is adding a smaller error to the enthalpy if you only evaluate at the saturated temperature without considering this term. That means the contribution of this term is very, very small, but however, it is important when you go for a particularly for a higher pressure conditions, and the temperature, saturated temperature condition is lower. So, you can look at this. So, if you look at if we compare this these things, that we will get that at a given pressure the what you call the temperature is less than the saturated temperature for a compressed liquid, and similarly for either a given pressure or a temperature, specific volume is less than the specific volume at saturated conditions, right. And in the similar way, the enthalpy is less than the saturated enthalpy at a given pressure and temperature. And this is just opposite of that of the superheated vapor, what we had seen earlier. So, now we have learnt how to handle the compressed liquid if the compressed liquid data is table is not available. If it is table is available, you can go directly and use it, okay, there is no problem. But if it is not available, you need not to worry, get worried, you need not to get worried about it, rather you can what you call use the saturated table corresponding to the temperature, not to the pressure. So, till now we have used the what you call a table the data thermodynamic properties in the tabular form, but however, it is not very elegant. It is a cumbersome to evaluate and other things. If you look at, if we can get a equation by which we can evaluate the data, it will be very important, and and also the accuracy will be very higher, provided if that equation itself is accurate to predict the data. And in modern times, you can also use that for your modeling. If it is equation is there, it will be easier. people have attempted to find out the relationship between the pressure, temperature and the volume, and that we call is basically equation of state. And most of you are aware and you have used left and right, that is the equation of state for an ideal gas, right. And that equation predicts basically the pressure, volume, temperature, behavior of a gas quite accurately within certain properly selected region. That means, equation of state what we have used, or ideal gas law what we call, is being utilized only for ideal gas, and that is equal to P V is equal to N R U T, and where R U is the universal gas constant, and which is equal to 8.314 kilojoule per kilomole Kelvin. That you are all familiar with from background. And if I can use also specific gas constant, that is R, and can be related to universal gas constant R U and molecular weight. A specific gas constant is basically equal to R U divided by molecular weight, and its unit will be kilojoule per kg and Kelvin kind of things. And different substance have different specific gas constants. If you look at like air, is having 0.287 kilojoule per kg Kelvin, and whereas the helium is a very high value, that is 2.0769, and of course, the nitrogen is very closer to the air, and of course, argon is little away from the air, that is 0.2081. And this like equation can be written in various form, because we know that volume is basically if you look at, is equal to number of moles into specific volume, and if I can put these values here, okay, in the equation of state P V is equal to N R T, then I can get P nu cap is equal to R U T. So, this is basically another form of equation of state, and from this equation P V is equal to N R I 2, if I can do, I can multiply the molecular weight here and also divide by molecular weight, and this is nothing but your what you call R, right, and this is nothing but your M. So, I get P V is equal to M R T, and if you look at, then I can say volume per unit mass, this is nothing but specific volume, and this is P V is equal to R T. I can write it down this as also P is equal to rho R T, right. This is 1 over nu is nothing but your the density, right. So, various forms one can use of ideal gas law, which most of you will be familiar with, and we will have to see what are the limitation of this gas law, right, because this gas law is valid for the what you call low pressure and high temperature gases. Question arises why it is so, and when we can call it as basically the pressure should be low. For example, if I consider 1 atmospheric is a low pressure, or 100 atmospheric pressure is a low for air, or it will be 200 atmospheric pressure, and temperature whether the ambient temperature is high, or I can say look 500 degrees Celsius is high, or I can say that look 1000 degrees Celsius high. That those things we need to know, and how we will evaluate that we will talk about, and where this ideal gas law will be valid. Because unless we know where it will valid, we do not know where to use. So, from the kinetic theory of gases, for an ideal gas, we know that molecules do not occupy any volume. That is the premises based on which this ideal gas law is derived. But however, the molecule will be having what you call certain volume. If the pressure is very high, then what will happen? These molecules actually the volume occupied by these molecules will be not comparable, at least a larger portion of the volume where the gas is contained. So, then this ideal gas law may not be valid, and also it is being devised, ideal gas law will be valid only when there is no attractive forces between molecules, but however, the molecules will be having attractive forces, right. And when it will be valid? When the molecules is very far away from each other, then the attractive forces will not be there, and this can be possible only when either the temperature will be very high or the pressure will be low. So, right. So, therefore, that is the things what it will be having. For example, like as I told, like let us consider air at 298 Kelvin and pressure is around what you call 100 kilopascals kind of things, atmospheric pressure you can say roughly. And so, number of molecules per meter cube will be something 2.4 into 10 power 25. And if you look at the volume available per molecule will be what? 1 over divided by 2.4 10 power 25 will give me 4 into 10 power minus 24 meter cube. That means, each molecule will be occupying this amount of what you call volume, which is quite small as if you look at it. So, if you consider the diameter of each molecule approximately 2 into 10 power minus 10 meter, and if you consider it to be spherical, and then you can find out volume, right. Then it will be something, volume of each molecule will be 4 into 10 power minus 27, right. If you divide this term, what you call this volume available per molecule divided by the volume of each molecule, then you will find volume occupied by each molecule will be 1000 of the free available volume, right, and which you can say that it is negligibly small, because it is something 1000 times less than that, it is a, one can say that, and hence molecule do not occupy any volume approximately, you can say that way, because they are very tiny numbers, right. And the distance between two molecules will be something 10 power minus 8 meter, of course, that is at atmospheric pressure, and the distance between two molecules will be something 50 times of the diameter of the molecule, right. So, you can say 50 times apart, and then the intermolecular forces will not be really existing between, but or it is a very small force will be existing between two molecules, which is negligibly small. So, therefore, we can happily say that ideal gas law can be valid at ambient pressure and temperature. If you consider the air, we have taken the example of air, not only the air, but nitrogen, oxygen, hydrogen, helium, air, and even the heavier gases like CO2 can be treated as ideal gas in the range of certain pressure and temperature, certainly in the ambient pressure and temperature. But we need to look at what is that practical temperature where we can have use this ideal gas law, and keeping the error incurred because of use of this ideal gas law, where we have assumed that molecules do not occupy any volume and there is no attractive forces between the molecules. So, question then arises, we will be dealing with water vapor, particularly when we are dealing with the steam power plant, right, or we will be also looking at a refrigeration air conditioning system where we will be considering the vapor, and its liquid mixtures. And we may be considering also, particularly when we are looking at some kind of a steam what you call hydraulic turbine, even some vaporization will be occurring, even in hydrogen due to the low pressure, then also. And the two phase fluid will be using even in our atmosphere. For example, like day before yesterday there was a shower, right, and then the air will be moist and the air will be containing not only the oxygen, nitrogen, also the water vapor. So, how to evaluate those properties, So, whether question arises water vapor can be treated as an ideal gas or not. So, let us consider this, right. If you look at, we are using again this T and V diagram here, and these are the wet mixtures we can consider here, where ideal gas we can assume here. In this regime, because the temperature is high and the pressure is what you call maybe little low also, we can look at it. And at even pressure below the 10 kPa, water vapor can be treated as an ideal gas regardless of its temperature, with a negligible error like 0.1%. I mean, you can say, look, I am not bothered about 0.1%, because in engineering sense 3 to 4% error is not really much, right. So, at high pressure, however, ideal gas assumption yields unacceptable error, particularly in the vicinity of critical point. If you look at these values, whatever it is given here, these values are basically indicates error. If you look at critical point will be somewhere here, the error is very, very high. If you look at something here, it is 271 percentage error, and this is 56 point, and this is, if you look at 152.7, and it is quite, you cannot really consider this region like unacceptable, particularly vicinity of critical points. And so also in this region, is a very, very high regions where the vapor will be existing, however, the error will be enormous. So, in air conditioning applications, as I told, the water vapor in the air can be treated as an ideal gas or not. Whether one can assume? We can definitely, because the vapor, whatever it is there in the air will be very, very less, and it is at ambient temperature kind of things, and also the ambient pressure. So, therefore, we can use the ideal gas law. And can I use the ideal gas law for steam power plant application? Because the steam power plant applications, or in steam power plant, the pressure will be very high, right. So, therefore, one has to be careful to use ideal gas law, because the ideal gas law will incur a lot of error, and one must not use the ideal gas law, rather to get into the steam table to evaluate the properties. And as I told you, this percentage error, this V table you can use, and this is from the ideal, and divide V table into multiplied, it will give you this thing. And of course, this ideal is basically assuming ideal gas, that will where steam can be treated an ideal gas when it is less than 1% error. For example, in this region one can use the kind of a 1% error kind of thing, but however, in this region, right, if you look at, one should not, if you are having steam here, one should not use this region, because error is much higher. So, we will we have seen in this lecture how to handle the superheated steam table, and how to use the data when the compressed liquid table is not available by using the saturated steam table, and then we have looked at ideal gas law and its applicability, where we can use, where we cannot, and why it is so, that we have seen. And in the next lecture, we will be looking at basically the better equation of states apart from the ideal gas law, and we will proceed on that. Thank you very much.